Hello, thank you very much for tuning into this workshop on upcycling of various waste streams into high value and high performing products. And hopefully we can move towards sustainable development with these type of research. My name is Syed Ghaffar. I work at Brunel University London, and my research is around low carbon engineering materials, combining it with innovative technologies in order to be able to get towards sustainable development and reach milestones which are very helpful for our future generations. So first of all, I would like to speak about revolution and transformation and what are the differences between the two. We have to focus on introduction of automation and digital technologies. This is a hot topic that everybody has been talking about for the past few years, is gaining a lot of momentum amongst the practitioners, amongst the industry and researchers. We have to be able to use the digital technologies to our advantage to record and keep a log of all the information, for example, of the materials that we have in the building, in this room, for the future purposes. We have plenty of different breakthrough technologies that have already shown to have good potential in transforming our sector. The construction sector, unfortunately, is known to be decades behind our other sectors, such as automotive, biomedical, computer. And we need to adopt and implement more breakthrough technologies, such as cobots, autonomous vehicles for construction activities, autonomous maintenance, autonomous diagnostics, autonomous monitoring, such as the drones. And construction 4.0 is really what we need to move towards. Construction 4.0 is a new concept that is gaining a lot of attention. It's basically a combination of several or many technologies that are transformative, such as digital technologies, such as building information modeling, drones, robotics, 3D printing, VR, AR, virtual reality, augmented reality, in order to be able to transform and make the construction processes more efficient. And all of this hopefully will be contributing towards sustainable development. So this is some facts that I would like to present to you as the built environment facing a lot of challenges ahead, and these are the reasons why we need to move towards transformative technologies. As one of the major sectors and cornerstones for economic competitiveness and the social well-being of the citizen, the built environment sector is one of the least digitized and automated sectors. So this is the huge problem that we have. The built environment is overwhelmed with inefficiencies, low productivities, resource wastage, and environmental issues. These are all associated with poorly planned developments, excessive developments. It's difficult to invest in R&D. The construction sector's profit margins are very, very low, extremely low, around 1 to 2, 1 to 5, or much lower than 5%, depending on the kind of project that you're involved in. With the industrial collaborators that I speak to, their construction projects, their infrastructure projects have very, very low margins. So this means that the breakthrough technologies require high initial capital, and because of these low profit margins, we have less investment, less potential, less possibility for investment in R&D, research and development. So the call of action of the built environment is driven by the need to become more sustainable, and it evolve into an industry, a sector where data is used and interpreted in a way that we can improve our decision making. It is important for our industry to work closely together. We need to have industrial symbiosis to drive this transformation, minimize the impacts of construction industry on the environment. So one of the important topics where the digitalization or the use of breakthrough technologies can really be helpful is in waste management. So let's dive into this topic on waste management and what it is. So there are different trends in waste generation. Population growth in cities means we will have a lot more waste generated. Per capita income increases impact time and amount of waste generated. More waste equals to more government costs, and oversights increases. So a waste management system is streamlined process used to dispose, reduce, reuse, and hopefully prevent waste going to landfill. It is also an approach where companies implement comprehensive strategies to efficiently manage waste from their origin until their final disposal. Possible waste disposal methods, of course, are recycling, composting, incineration to recover energy, landfill, bioremediation, waste to energy, and waste minimization. So we need to adopt a circular economy approach where there are plenty of different ways that we can move away from that linear economy and linear way of consuming and creating waste. So we have extraction of natural resources, we make the product, we use the product, and then afterwards they are called waste, and we dispose of them without any recovery, without any resource recovery, without any recycling and circular thinking mentality. So we have the product use, we can share and reuse many times, we can do minimal handling of the waste in order to be able to process the materials and recover more and then make more products. So resource recovery, secondary raw materials recovery is extremely important. So whenever I want to talk about the environmental impact, I show this type of very simple graph that is using a description of different ways of managing waste and the environmental impact. So if we reduce the waste, of course, we have the lowest environmental impact. Reusing, recycling is still associated with some energy consumption. So it is in the range of medium in terms of environmental impact from low to high. We have compost, incineration, and landfill, and of course, are the ones with highest environmental impact, especially then we are running out of landfill spaces. For our industry, for the built environment, the construction demolition waste is the most sort of related and the biggest headache for industry practitioners. So what is CDW? It's a combination of excess materials coming from site construction, clearance, excavation, refurbishment, renovation, demolition, and roadworks. Or it could be actually caused or generated from natural disasters such as earthquakes, floods, hurricanes, and tsunamis. This diagram here shows the sort of another representation of what construction demolition waste is made out of man-made sources, public works, construction and maintenance, building construction works, and renovation works. And if we have earthquakes, floods, hurricanes, and tsunamis, we will also have, in an unfortunate disaster, we will have a lot of waste, construction and demolition waste. The materials that we will find in CW include aggregates, concrete blocks, stone, gypsum, wood, glass, ferrous, asphalt, radial ballast, papers, and maybe some asbestos, which are very, very extremely dangerous and hazardous. CDW is one of the heaviest waste streams generated in the EU. It accounts for approximately 25% to 30% of all the waste generated in the region. It consists of numerous materials, as I covered in the previous slide. Concrete, bricks, gypsum, wood, glass, metals are amongst the highest percentage in this waste, construction demolition waste. And this pie chart shows the breakdown of a typical CDW. Most of it, depending on where you are, but actually it's concrete. And you have 30% ceramics, bricks, 10% metals, 10% wood, and other type of different waste that you could have in CDW. So in my research, I've been looking at natural sand replacement with a variety of different waste streams, such as polyvinyl chloride. This is a plastic. So we have used hard PVC coming from the pipes, as you can see in the diagram. We have used soft PVC coming from electronic waste, the cable covering. We have used tire rubber from these vehicles that have been written off, glass from beverages, bricks from construction and demolition waste. And we have also used geopolymers that have been made for scientific purpose, for testing and scientific purposes. And then we have been able to re-examine their potential in the production of new concrete. And these pictures that you see on the bottom of this slide are all the samples that we have made with these type of sort of aggregates. So these are recycled aggregates coming from different waste streams, plastic, polymers, glass, ceramics, and geopolymers inside new low carbon concrete material. And this is a cross section after the testing of these concrete blocks, and you can see the presentation or representation of these waste bricks inside the material. Some of the results from this research are included in this slide, but just let me open up the testing program. We had alkali activated materials. We used alkali activated materials. We used GGBS, which comes from the steel manufacturing. We used silica sand, fly ash, which is from the coal burning plants, which we are running out of. Thankfully, all the coal burning plants are shut down. So the supply of fly ash, which is a byproduct of burning coal, is very, very low in certain regions in the world, especially in Europe and the UK. So that's our binder, alkali activated binder. We use some additives in order to improve the rheology, in order to improve the workability and the strength of our materials. Very small percentages of these additives at a ball joint, which is a type of nanoclay. We use very, very small percentages. And for the aggregates, we use natural sand as our control sample benchmark. We use recycled PVC aggregates, polyvinyl chloride, and we use also rubber aggregates to replace sand. Our replacement ratios were 30%, 50%, and 70%. We test the concrete blocks developed from these recycled aggregates for a variety of parameters and properties, such as durability, microstructure, physical properties, and mechanical properties. You can look at the scanning electron microscopy of these aggregates. On the left-hand side of the slide, you are looking at rubber. So it has a much more smooth surface and sharp edges. And on the right-hand side of the slide, you're looking at the recycled aggregate of PVC, polyvinyl chloride, which has got a lot rougher surface and serrated edges. Quite different to the microstructure of rubber. So they differ quite a lot in terms of morphology when it comes to their microstructure in 500 micrometers. We looked at the flexural strength and the compressive strength, and you can see that the flexural strength and compressive strength both reduce with increasing the amount of recycled aggregates. And this is something to be expected. We are saving natural sands because our natural resources are in scarcity, and we need to think of alternative ways. So these graphs show that if you want to replace sand with recycled aggregates, you need to focus on non-load bearing structures, on other applications, noise reduction walls, for pavements in the recreational areas in parks, because they have very high impact and absorption, energy absorption. But you can see that if you use 70%, for example, of rubber or PVC at 7 days of strength or 90 days of strength, we are getting very low compressive strength of around 10 to 20 MPa. And 70% replacement by volume is the highest replacement ratio that we went to. So it's 70% recycled aggregates and 30% is sand. Instead of having 100% sand and gaining very high compressive strength, for example, we can have only 30% sand and get a very moderate compressive strength, use it for non-structural load bearing applications. So by no means we are here saying that we have developed a structural load bearing product. No, we are working towards sustainable development, and we are also managing the waste that could have gone to landfill, the tires that could have gone to landfill, and the plastic that is gone to landfill. And we know about the problems that we have if we send a waste to landfill, especially with chloride. These images here are showing the interfacial bonding between recycled rubber and PVC. And you can see on the top hand side of the pictures, on the top part of the slides, that the PVC particles have much better or intimate interfacial bonding with the alkali activated matrix, so with the GGBS and fly ash activated using alkali activators. They have much more compact microstructure, which means why they have a better strength, compression or inflectional compared to rubber. And in the rubber, we can see some delamination between the surface of the rubber particle and the matrix. So this delamination explains why their mechanical properties is very low, whereas in the case of sand, natural sand, of course, we don't see this delamination in the microstructure, and therefore we can focus on the non-load bearing applications. Sound reduction, sound absorption, wall panels, which are used for highways, motorways to reduce the sound absorption. Very important, we looked at the equivalent CO2 emissions, kg CO2 per ton of our developed materials using PVC and rubber aggregates. And the gray bar is looking at the control sample. So a sample which has been made from 100% sand. You can see that the ECO2 emissions is 230 kilogram per ton. Whereas in the case of 30% replacement, that value is a lot less. 50% is a lot less, and in 70% it becomes negative. So we are preventing CO2 emission to the atmosphere if we use 70% of these aggregates that alternatively would have gone to landfill and replace them with natural sand. There are very interesting topics here about CDW sorting and processing, where we use innovative technologies such as a smart dismantling rather than complete demolition in order to be able to recover more resources from this system. Why do we need to recover more resources? As Thomas Rao said, every building is a material depot, and we need to look at it as a material bank. We need to be able to recover resources for the new project instead of just sending all the waste and treating them and naming them waste. We also looked at my research group looked at the pathways to circular construction and integrated management of construction and demolition waste for secondary resource recovery. The publication is there. You can have a look at it. The link is provided. But the main outcome, we studied the bottlenecks in circular construction within the UK context, UK construction context. And we asked a lot of stakeholders in the industry who are at managerial level, health and safety managers, sustainability managers, construction demolition workers, construction demolition decision makers. These were very relevant stakeholders who had, 15 or 25 years, or some of them 30 years of experience in the industry. We asked them what are the biggest setbacks towards the recycling or reuse of CDW, construction demolition waste. And 41% of them mentioned the logistics. So getting the site sorted and taking it to another recycling part. The logistics is difficult. So why not have on-site sorting, on-site recycling? If this space allows, we can use these mobile platforms for crushing concrete at the same site. So the logistics is no longer the problem. Some people, 29% of the stakeholders mentioned the cost. 12% mentioned the health and safety regulations, and 12% also mentioned the time. We also asked them, where do you see improvements in the recycling process? And as expected, one of the options on our questionnaires was on-site operation, and 44% of the stakeholders really like it, and they strongly believe that with mobile on-site platforms, concrete crushers, or other type of mechanical crushers that can handle or reduce the size of waste into recovered aggregates, into recovered fibers, is the main investment or improvements that we can have in order to improve the circular construction. So the study also revealed that legislations by the government are extremely important on the reuse and recycling threshold that can bring circularity within the built environment. We need to focus on smart dismantling, as I mentioned, as opposed to do complete demolition, with innovative ways in setting benchmarks in circular construction. And we must think about the harmonized technological and non-technological solution, which brings us to a closed loop material processes and a circular economy. So this model here really summarizes what we need. Starts from the top, waste identification and source separation. We must have a pre-demolition audits, use robotic sorting and processing, have mobile site, on-site operations, think about remanufacturing processes on-site or off-site, pilot validations, quality management, and policy and regulations are also extremely important. So the key takeaway message from my workshop here today, hopefully, is that we need creative ideas to reduce the waste streams from the construction sector, save the Earth's natural resources, and deliver net zero carbon.